3.4, it's called Proofs with Perpendicular Lines. You guys ready? Okay. Proof with perpendicular lines, and basically we're learning some more theorems, but these ones are all going to have to do with lines being perpendicular, and different ways we can use them in proofs. Now, before we get too far into it, we need to understand if I am trying to find the distance from point A to line L, there's a special way to do it. Okay, you wrote down the definition last week. If you don't remember the definition, you need to have your book open anyways, and you need to be looking at the definition. What is special if I want to find the distance from point A to line L? What do I have to make sure I do? Okay, just any point? You're right. The point where it is perpendicular. So if I'm measuring from point A to line L, I have to measure in a way that, if, let's say I was using a ruler, would have to be perpendicular to the line. Okay? Because if I don't do that, Paul might measure it here, Bo might measure it here, Emma might measure it over here. They're all going to be different, right? Okay, well, the distance from one thing to another should always be the same no matter who measures it, correct? Okay, so if we just always use the fact that the distance is perpendicular, which would also be the shortest distance, right? Okay, then we will always all be on the same page. So, using that idea, if I were to draw a triangle like this, and I labeled this as point D, B, C, A, and I give you coordinates of -1, 8, 6, -3, -4, 2, and -6, 3. Give you a second, copy those down. Directions say find the distance from point A to segment BC. How would I do that? Okay, yeah, let's say I can't use a ruler. I use the distance formula. Okay. The most common mistake on this is people tell me that I find the length of AB or AC because I'm talking about B and C. Okay. Why is that incorrect? Because it's not perpendicular. That's not my shortest distance to segment BC. Okay. So I need to find the length of what segment? AD. And just like Jersey said, we have to do it using the distance formula. So this will be a good refresher on that. What is the distance formula? Just before we plug anything in. Okay. And Tegan, I noticed you were doing the y's first. It doesn't matter. If you do y2 minus y1 plus x2 minus x1, it's going to end up the same because you're going to add them together anyways, right? Okay, so that doesn't matter. All right, so what is x2 then? could it be -1? Yeah, it just depends on how you start, right? It doesn't matter. So I have -4 minus x1 minus a -1. I'm just going to leave it like that for now. Okay, and then plus y2 is 2 minus 8 squared. Okay, now the diagram doesn't even matter anymore. So I have my distance here. -4, and you said that was plus. Okay, so -4 plus 1. -3 squared. And I'm writing out every step. You might not write quite as many as I do. 2 minus 8. -6 squared. -3 squared is plus 36 equals 45. I'm going to plug that into my big ideas, and it's going to say I'm wrong. Why? Because I need the square root. Okay? I did that on purpose because I had a student on Thursday or Friday, I can't remember, and I honestly don't even remember who it was, but I remember they were working on a distance problem. I don't remember if it was algebra 2 or geometry, but they were working on a distance formula problem, and they told me that I've done this 5 times and I keep getting the wrong answer. This is what they were doing. Okay, and I specifically remember warning you guys about this, that that's the most common mistake with distance formula, is you lose your square root. Okay? In the other classes, I counted out how long it takes you to write those 3 extra square roots. It was less than 3 seconds. 1 1,000, 2 1,000, 3 1,000. You get what I'm getting at? Don't be lazy. Just write the square roots. Okay? You will literally, by not doing it, save less than 3 seconds of your life. I don't think you'll miss it. I think you'll be okay. Okay, so go ahead and write those above there so you don't forget. Now, I believe that your directions on your homework specifically say round to the nearest tenth. So if they do say that, round to the nearest tenth. If they do not say that, can you leave your answer as a radical? Yes. I think they do say round to the nearest tenth. So then you would end up rounding that, and I'm just going to do it for you. It ends up as 6.7 approximately units. Okay? But if it does not say round to the nearest tenth, then just leave it as a radical. Okay, just a good refresher there on distance formula. Questions on that? All right, now the next thing they talked about in this lesson, which was your second vocab term that you wrote down last week, was a perpendicular bisector. Okay. We have worked with each of these words separately, right? What does it take for 2 lines to be perpendicular? They form a right angle. Okay, so if I have segment AB, is it perpendicular to line L if it forms a right angle? Yes. Okay, so that takes care of that part, right? Okay. What did it mean to be a bisector? It splits it in half. So then AC would be congruent to CB, right? That takes care of the bisector. So if it's a perpendicular bisector, it forms a right angle and splits the segment in half. Okay, it does both of those things. So we've worked with each word separately. Now we put it together or combine them together for a perpendicular bisector. Okay. So if that's a right angle, 90 degrees, what's this angle down here? Right angle, 90 degrees. And this one? Same. Same. What do you do if I give you this problem? These are the segment lengths. 3x plus 4 equals x minus 2. We'd set them equal to each other because they're both the same length. They're congruent, right? And they'd do a better job probably of labeling whether they were angles or segments. Okay? We can handle that, right? Not too bad. Okay. All right, flipping over to the 3 theorems which are the main part of this lesson. The 3 theorems you wrote down. If you don't have your theorem sheet out, get it out now, because I've found that every other class has needed them while we're talking about this. Okay. The first theorem is called the linear pair perpendicular theorem. Okay. Again, you should be able to kind of break down what's going to happen here just by reading the name. I'm going to have a linear pair and what? And a perpendicular intersection between 2 lines or segments or something, right? Okay? So, what this theorem actually tells us is that if I have a linear pair and those angles are congruent to each other, let's go ahead and just make this a line, then those 2 lines must be perpendicular. What do you know about 1 and 2 if they're a linear pair? They add to 180 degrees, right? Can we all agree with that? If they're a linear pair, they have to add to 180. Okay? Well, if they're congruent, they both have to be 90, right? Because if they're not both 90, then they can't equal 180 if they're the same. Right? Agreed? Okay? So, that's this theorem. It says that if I have a congruent linear pair, meaning I have a linear pair and the angles are congruent to each other, if that's the case, my lines have to be perpendicular. Okay, which, like we said, that makes sense because they both have to be 90, which would make it perpendicular. Okay? So in this case, if I want to write this, M would have to be perpendicular to L. Okay. The next theorem, perpendicular transversal theorem, just reading the name, obviously I'm going to have a transversal, so I'm going to have something that looks like what I have over here, right? Because this is my transversal. So I'm going to have a transversal, and it's going to have to be perpendicular to something, correct? Okay. And again, I'm not going through and writing all these words because you should already have these on your theorem sheet. So as I read them, you should understand what I'm talking about. Okay, I'll label these lines L, M, and N. And it does tell me that these lines are parallel and that this is a right angle. Okay. This theorem, the perpendicular transversal theorem, tells me that in a plane, if a transversal is perpendicular to one of 2 parallel lines, then it must be what? Exactly, perpendicular to the other one. Okay. So if a transversal is perpendicular to one of 2 parallel lines, it also has to be perpendicular to the other parallel line. Okay. Could you have gotten to that exact idea using a different theorem from section, bless you, 2, I think it is, maybe 1, not for sure, of chapter 3. Why else would those 2 angles have to be congruent to each other? Corresponding angles theorem. The lines are parallel, so corresponding angles must be congruent, right? Okay, so you could have gotten there. Now, technically, in a proof, it would have taken a lot longer because they told us these lines are perpendicular. So then we'd have had to say that it's a right angle. Then we'd have had to say it's 90 degrees. Then we'd have had to say corresponding angle says this is 90 degrees. And then we'd have had to say it's a right angle. And then we'd have had to say that they're perpendicular. Okay, so there's a lot of technical steps that we'd have had to go through to get to this, but we could have proved this if we needed to. Okay, so this theorem is going to cut out 4 or 5 different steps. Okay, and I know it makes sense to you guys because I've talked to some of you about it in the past. We just didn't have this theorem yet. Okay, so if a transversal is perpendicular to one of 2 parallel lines, it has to be perpendicular to the other as well. Okay. Now the last theorem we have technically is just the converse of this. Lines perpendicular to a transversal theorem. Make sure I named that right. Lines perpendicular, yes. Okay, and I'm going to draw the same diagram I just drew. It's different than what they have in the book, but I want to draw the same one so you can compare the differences easier. And I have lines L, M, and N. And in this case, that's what we know. Okay, we know our transversal is perpendicular to both of those lines. Okay. This theorem tells us that if a transversal is perpendicular to 2 lines, then those lines must be what? They must be parallel to each other. Okay. If a transversal is perpendicular to 2 lines, those lines must be parallel to each other. Okay. In a long roundabout way, you could have used the corresponding angles converse. Okay, it would have just taken you twice as many steps. Okay, but it's telling you the same thing. You're getting to the same point. M must be parallel to N if the transversal is perpendicular to both of them. Okay. Here's a little test for you guys. I haven't had anybody answer correctly yet today. Including this theorem, how many theorems do we have to prove lines parallel? Sure. It should be easy to count if you did what I asked you to. Sophia? Yes. Thought you were going to give me an answer. Yes, you are. Hopefully Emma's counting, so I'm going to call on her.
No, I don't know what they're counting.
Okay, what'd you count?
7?
Nope, not quite.
No,
Less.
5? 6.
There's 6. Okay, so let's go through them. Let's do the 5 that we had not including this one. Jersey, give me 1. You guys paying attention?
Alternate interior angles converse.
Alternate interior angles converse. William? She just did alternate interior angles converse. Alternate exterior angles converse. Oh yeah. Emma? Consecutive interior angles converse. Paul? We did alternate interior, alternate exterior, and consecutive. We just did consecutive interior. What's the other one? No. Look on your theorem sheet. Do you have them labeled as proving lines parallel? Okay. Taken? Okay. Corresponding angles, converse. So that takes care of our 4 converses, right? Okay, William? Transitive parallel lines. So those are the 5 from last week. Plus this one, lines perpendicular to a transversal theorem. Okay, now we have 6. Okay? Just like you labeled the other 5, you should probably somehow mark this. Okay? That way when you're doing a proof and you're proving lines parallel, you are only looking at 6 different options. Okay, so you don't have to look through your whole theorem sheet. You just go to those 6 that we've talked about. Those are your only options for proving lines parallel to each other. Okay. The last example I want to do man. No, I'll never get this to work. Yeah. It's not what I wanted, but I can make it work. There we go. I got what I needed now. Oh, and can you guys tell that this is A here and this is E? Let me move. There we go. They want to know in this diagram which lines, if any, must be parallel to each other. Okay. Casey, Tegan, Sophia, Jersey say that A and B must be parallel to each other. Why? What theorem if you're doing it in a proof? Lines perpendicular to a transversal theorem. I have 2 lines, A and B, that are both perpendicular to their transversal D. So they must be parallel to each other, correct? Are there any more? Possibly C and D, but do we have enough to prove it? No. Okay, so I agree with Casey. Possibly C and D. But to be able to say for sure, I have to have enough information, right? Okay, we actually don't really know much about C. It looks like it's parallel to D, but for all I know, maybe it's just like slightly off, right? Or maybe it's slightly off this way, whatever. I don't know, because I don't know any of these angle measures up here on C. Okay, so C and D might be, but we do not have enough information to be able to say for sure that they are. Okay? Questions?